Welcome to Mathematical Physics. Today, we are going to explore higher-order homogeneous ordinary differential equations. Do not let the long name intimidate you. By the end of this video, you will understand exactly what these equations are, why they are the secret to understanding how the universe balances itself, and how to solve them, step by step. Before we look at any math, let us build our intuition. Imagine a playground swing on a quiet day. If you pull it back and let it go without pushing it again, its motion is determined entirely by its own weight and the length of its ropes. In physics, we call this a free or unforced system. When we write mathematical equations to describe such isolated systems, they are called homogeneous differential equations. The term higher order simply means we are looking at rates of change, like acceleration, instead of just velocity. Now that we have a physical picture, let us define this formally. A higher-order linear, homogeneous, ordinary differential equation involves an unknown function and its derivatives. The word linear means these derivatives appear only to the first power. They are never squared or trapped inside a sine wave. Homogeneous means every single term contains the unknown function or its derivative, so the whole equation equals 0 when moved to one side. We will focus on constant coefficients, meaning the numbers multiplying our derivatives are just fixed real numbers, not changing variables. You might be wondering why we care so deeply about these specific equations. The answer is that almost every stable physical system near its equilibrium point can be described by them. If you want to design a car suspension system that absorbs bumps without bouncing forever, you need these equations. If you are building an electrical circuit for a radio receiver, the exact same mathematics applies to the flow of electrons. They are the universal language for describing how things settle down or oscillate when left completely alone. This brings us to the general mathematical representation of these systems. Here is what the equation looks like on paper. The variable y represents the unknown function we want to find, such as the position of a mass or the voltage in a circuit. The variable x is our independent variable, which is usually time or distance. The symbols a sub n down to a sub 0 represent constant real numbers. These constants correspond directly to physical properties, like mass, friction, or spring stiffness. Finally, the 0 on the right side is what makes it homogeneous, physically meaning there is no external driving force acting on the system. To solve this daunting differential equation, we use a brilliant mathematical trick. We guess that the solution looks like an exponential function, specifically e to the power of r times x. When we plug this guess into our differential equation, the derivatives pull down powers of r. This beautifully transforms our difficult calculus problem into a simple algebra problem. This resulting algebraic equation is called the characteristic equation. The symbol r represents the roots we need to find, and its values will dictate exactly how the physical system behaves. If r is positive, the system grows exponentially, and if r is negative, it settles down to rest. Let us see this strategy in action with a concrete example. We're given a second-order equation and asked to find the general solution for the function y. We start by converting the differential equation into its characteristic algebraic equation. The second derivative becomes r squared, the first derivative becomes minus 5r, and the original function becomes just the constant 6. We then factor this quadratic equation to find the roots. Solving this gives us r equals 2 and r equals 3. Now that we have found our roots, r equals 2 and r equals 3, what do we do with them? Because these are two distinct real numbers, it means our physical system has two different modes of exponential growth. To form the most general solution possible, we combine these two independent solutions using arbitrary constants, C1 and C2. This combination is known as the principle of superposition. Physically, because the exponents are positive, this represents a system whose output grows rapidly over time, like an uncontrolled chain reaction. We just saw what happens with real roots. But what if a system has a restoring force, but absolutely no damping or friction? This brings us to the simple harmonic oscillator equation. Here, the second derivative represents the acceleration of a mass, and the positive 9y represents the restoring force of a spring, pulling it back. Notice that there is no first derivative term in this equation, which physically means there is no friction to slow the system down. Let us see what happens to our characteristic equation in this specific scenario, and how it changes the math. Let us solve this frictionless system step by step. Just like before, we will write down the characteristic equation by replacing the second derivative with r squared. Moving the positive 9 to the right side gives us r squared equals -9. Notice that we are now looking for a number that, when squared, gives a negative result. Taking the square root of both sides gives us an imaginary number, specifically positive and -3i. In the context of differential equations, an imaginary root always means that the physical system will oscillate or vibrate continuously. We have our imaginary roots, but how do we graph an imaginary exponential? This is where we use Euler's formula to convert complex exponentials into sines and cosines. The complex solutions transform into a combination of sine and cosine waves. The number 3 inside the trigonometric functions is the angular frequency, telling us exactly how fast the system oscillates. Because there is no real part to the root, the oscillations will neither grow nor decay. This perfectly describes a system that bounces back and forth forever without losing energy. Let us bring all of this together visually. On this graph, the horizontal axis represents time, and the vertical axis represents the amplitude or position of our system. Look at the dotted line shooting upwards. This represents real positive roots, an unstable system growing out of control. The dashed line curving gently towards zero shows real negative roots, an overdamped system settling to rest. Finally, the solid wavy line represents complex roots, showing pure oscillation. The roots of the characteristic equation literally draw the future of the system. We have covered a lot of ground today, so let us summarize the most important ideas. First, higher-order homogeneous equations are the mathematical engines for unforced physical systems. Second, by guessing an exponential solution, we transform difficult calculus into straightforward algebra using the characteristic equation. Finally, the roots of that algebraic equation tell the entire story. Real roots mean exponential growth or decay, while complex roots mean the system will oscillate. Mastering this gives you the key to understanding everything from mechanical vibrations to quantum mechanics. Great job today!